Hey guys, so we are looking at 2.2 notes. You should get a copy of this piece of paper if you haven't, so make sure you do that. Okay. So jumping over here to the first question, it says, given, I don't know why this is so blurry, given that angle 1 is congruent to angle 2, prove that angle L is congruent, or that line L is congruent to line M. So I talked about this super briefly, but the whole point of section 2.2 is to go backwards from where we were. So we were saying here are congruent segments, so therefore we have congruent lines. I'm sorry, here are parallel lines, so therefore we have congruent angles, and we could kind of pick up everything. We're going backwards. Okay, so if we're going to do a proof, we're going to always start, we're going to do a statement and reason. Okay, so when I ask to do a very formal one, this is what we do. Okay, and here they're going to ask us to do some steps. Well, first off, we almost always put down the given first. Okay, that angle 1 is congruent to angle 2. And we do have a theorem that says that if alternate interior angles are congruent, then those lines are parallel. But we're going to, I don't know, for funsies, we're going to add a step in here. And I'm going to go ahead and say that angle 1 is congruent to angle 3. What lets me say that? Because these are vertical angles. And again, I like to abbreviate, so that's how I abbreviate angles. And then we're going to go ahead and say, well, therefore, angle 2 must be congruent to angle 3, okay, because of substitution here. So we can go ahead and just write substitution or sub, abbreviate. And then finally, that means if angle 2 and angle 3 are congruent, then we can say that line L is parallel to line M. And the reason is because of the corresponding parts, but we're going to say the converse, and that's really this whole section's about, the converse of corresponding parts theorem, or I think it's a postulate actually. Okay, so converse just means going backwards. And honestly, if on the test you didn't write converse, I probably wouldn't fuss. And these proofs in this chapter are kind of, there's really not much to them. And honestly, we could have just said, if angle 1 is congruent to angle 2, right off the bat, then we could probably have said that these are parallel because of alternate interior. Okay, the textbook has us do this extra step. It doesn't make it wrong, it just makes it different. I want to point out, and on this next page in our notes, that it simply shows what they say a flow proof is. If you want to circle that word there, those words, flow proof. So a flow proof is just another way of doing it. So instead of having this kind of rigid almost method where I have a statement and a reason, they just kind of, what they do is a flow proof. So they say this first, and that's given. They say this because of that. They say together they get this, and then finally they get this as their final answer. So there's nothing really to write down there. I just wanted to show you what they call a flow proof. I personally like this type of proof, and most people who have done geometry recognize proofs as this, where you give a statement and a reason. This is kind of hard because you might forget to put the reason, but basically all they do is they put the statement on top and they put the reason underneath, and then just kind of draw these arrows. I am not a fan at all of the flow proof, but I needed to show that to you so you weren't confused by that. And then finally, I'm going to have you, we're going to do a proof together. I really like this question, so I could see this proof showing up on the test as a proof you got to do. Okay, So first thing I want to do is I'm going to go ahead and name some points here. I'm going to go ahead and call that A and call that B. Okay. So given the following angles. So there's really nothing given here other than this shape. So what I'm going to do is I want to first just draw a line here. Okay. So first I'm going to say in our statement and reason. First I'm going to go ahead and say call this point here C and this point here D. Okay. And I'm going to go ahead and say I'm going to draw segment CD parallel to AB. Okay. And what I'm doing here is I'm going to just use the definition of parallel lines. Okay. So the definition of parallel line says that I'm allowed to basically that I just created these CD. Now, is it perfectly parallel? Mine is not. I just drew a line, but I'm allowed to say that this line exists such that these are parallel. Okay. And I could add another line up here that's parallel. So I've created a parallel line. Then if that's parallel, I'm going to go ahead and identify a point. Actually, I'm not going to even identify. I'm just going to say that angle, the measure of angle 2 is equal to the measure of angle BCD. Okay, so I just said that this right here is congruent to that. And the reason that's true is because of alternate interior angles postulate. Okay, which says that alternate interior angles are going to be equal or congruent. And then I'm going to say that angle, the measure of angle 1 is congruent or is equal to the measure of angle ACD. Okay, so now I'm saying that this right here is congruent to all of this right here, this big thing. And the reason I can say that is because of alternate interior angles postulate. It says that because I created this parallel line, I can do that. Then I need to say that angle A, I was going to say ACB, but I'm going to make that quicker. I'm going to say that the measure of angle 3, which is ACB, plus the measure of angle DCB is equal to the measure of angle, the big one, ACD. Okay. And I should have had all that on the left side. I just kind of ran out of room. And the reason I'm allowed to do that is because of angle addition postulate. Says that if you have two angles that make up a third, you're allowed to add them together. Okay. Well, I just said that angle ACD is equal to 1. So I'm going to replace that. I'm going to say measure of angle 3 plus, and I said up here that DCB, even though I wrote it backwards, is that this is equal to the measure of angle 2 from up here. And then I can say that, and this is equal to the measure of angle 1. Okay. And the reason I'm allowed to do that is because of substitution. And this is what I was trying to prove. Now, I wrote it in a different order, but that was what I was trying to prove. So that's that proof for why, and for why angle 1 is equal to adding angle 3 and 2 together. Okay. So that's what I want you to kind of see. And really, just to repeat real quickly, that 2.2 is basically just going backwards, where I tell you before I would say these lines are parallel, prove that this is, prove this. And now I'm saying this is true, so prove that. So you'll find that the homework and the quiz and all that is pretty similar to section 2.1. You have the rest of the period to work on that, and tomorrow is a work day. I'm gonna steal a little bit of that time tomorrow because I'm giving you so much time today to kind of finish up 2.2. I also want to point out that this proof right here would be a great one to have on our next test. I really like this one. I'm a big fan, and I went through it, so hopefully you can reference these notes again and watch this video again for the next test. All right, so again, go ahead and start working on 2.2 and any other thing you had to work on, and I'll see you tomorrow.